Hi everyone. I'm recording this video to show you my solutions to the midterm 2. Okay, so let's start from the first one. So the first one is BST. So well, if we have a node 10 and then the 10 will be the only node in the BST, so that's easy. And then if we insert 14 and remember the property of the BST, the binary search tree, the smaller value goes left and then the higher value goes right. So 14 is higher than 10, so it goes right. So it becomes the right child of 10. So how about 15? So 15 will be inserted to the right side of 14. So we have a BST like this. And for us, then we may find this BST looks ugly, right? So do we want to do a rotation? Do we want to balance the BST? Well, and it really depends on which version of the BST you are using. So if you have heard about the ABL tree, and for some of the data structure we cover this. So for an ABL tree, and yes, you have to do a rotation. Or if you are doing a RB tree, red black tree, and yes, we are going to do a rotation. But if we just use the most basic version of the BST, and then we are going to stay as is, because for this tree it doesn't break any of the property of the BST yet. So how about 8? So 8 is smaller than 10, so 8 comes here. So the next one, if we are deleting 50, and then well, who should be the candidate that will hold the position of 50? So well, the rule that covered in our textbook is we want to go to the right subtree, and then we want to find the smallest value in the right subtree, and then use that as a substitute. So we go to the right subtree, and the right subtree starts from the 75, and then well, how do we find the smallest value from the right subtree? So we go left, we go left, we go left again. So we are going to find the 52, and 52 will be the candidate that can take the position of the 50. And the good news is for the 52, it doesn't have any children, so we just remove the 52 from the existing location, and then we put the 52 here, and our work is done. So for a few of the students here in this class, and you pick the 30, and use 30 to substitute the value of the 50. So I would say it is okay because it doesn't break any BST property, but this is not what covered in our textbook. But I will agree with you, 30 can be a right candidate too in this problem. So the red-black tree. So for the red-black tree, and remember we are using this kind of the little boxes and to show they are the now pointers or the now leaves. Well, but we can still count them as the black nodes. Okay, so 10, well, just no children, so 2 black boxes. And then we insert 14. So the newly inserted node should be red node. So 14 will be a red node. And after that, well, how about 15? 15 inserted to the right side of 14, and then we have the red node and red node again. So now, well, it's no longer a valid a red-black tree, because number one, we have 2 consecutive red nodes, and number 2, well, it is already unbalanced. So we have to do a rotation, and after the rotation, and then 14 will be the root, and then we have 10 as red and 15 as red, so it's balanced again. Okay, the next part, and we are going to insert 8 to the left side of 10. So when we have the 8 here, now, well, the problem becomes harder because, well, we have 2 consecutive red nodes, 10 and 8. So how do we fix that? So, well, this triggers the case that for a newly inserted node 8, the parent is a red, and then the ankle is a red too. So in this case, we are going to change the parent and the ankle both to black, and then the grandpa will be red. So, well, this breaks another rule that of the RB tree, that is the root should always be black. So how do we fix that? So well, let me bring up this PowerPoint. So this is exactly the case we are dealing with. So we are inserting x, which is b, and then parent is red, and then ankle is red. So we are going to keep the new node as red, and then for the parent and ankle, they will be recolored to black, and then the grandpa becomes red. So how do we fix this C? And then, well, if we are following the algorithm says we are going to do a recursive call to fix up this C if there is any problem. But in our case, this 14 is already the root. So what's the solution? The solution is here. It is this line of code. So after we do all the cases of the fix-up, eventually, before we leave this insertion fix-up, there's one last thing to do. That is, if the, well, it doesn't matter if the root is black or red. Before we leave this method, we want to color the root to black again. So this will solve this problem. So after on this step, and then we are gonna stop doing the color fix-up, but we are gonna color the root, which is 14, into black again. So this solves the problem. Okay. So next, the time complexities. So hashing using division. Well, this is constant because we just send our key and then into a hash function, and then it will give me the location in constant time. And then using multiplication, the same thing. Well, this is the reason we are using hashing. So we send a key, and then the hash function will give me the corresponding location in a constant time. Okay, and then for arbitrary insertion. So for a arbitrary insertion, well, remember for the arbitrary, it will be kind of balanced. So it can't be super unbalanced. So this will be, the insertion will be a log n. And then how about the BST? So binary search tree. In the worst case of the binary search tree, it can be, for example, like we have 10, and then we have 14, we have 15, and then we have 18, and then 20, right? So if you are unlucky in this case, eventually you are gonna have a linear structure. So is this a valid binary search tree? The answer is yes. So if it's just a really basic version of the binary search tree, and then the worst case of doing the insertion is, for example, I'm inserting a 25, and then starting here. So 25 greater than 10, go right. And then 25 greater than 14, go right again. So we have to visit all the values before we can say, okay, 25, you are going to stay here. In this case, and we have to visit all the values in the BST, so the insertion will be a linear in the worst case. And then for the depth first search and then breadth first search, they will be OV plus E for both. Okay, and then for this graph, and how do we represent that in adjacency matrix? Well, we only have to represent the zeros and ones and showing if there is an edge from a node to the corresponding node. So, for example, there is a path from 0 to 1. So, if this row represents 0 and then 0 to 0, well, there's no way 0 goes to itself. But 0 to 1, yes. Well, and 0 to 2, yes again. So I'm just using zeros and ones to show whether there's a path going from one node to another. And then how about adjacency matrix, adjacency list? So it's kind of similar. So if for the first slot, and then we can go to from the node 0, we can go to 1, we can go to 2. Those are the only two nodes that we can go to, right? Okay, the next one, for a BFS, so breadth first search. So for the breadth first search, and this is the only correct answer. And if we just want to follow this graph, so we're starting from the 4, right? Starting from the 4, and then what are the nodes that we can go to in the step of 1? So we can go to 5, we can go to 1, we can go to 0. So if the cost of going to 4 is 0, and then the cost of going to 5, 1, 0 will be once. But how about 2? So this 2 can be accessed using 4, 1, and 2. And